Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life for 4 billion years? Perhaps not. When we talk about rare Earth, I think I would like to talk about rare solar system. Another possibility with the Fermi paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi paradox is just that the galaxy is so big. The distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. And perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. That's a possibility. One of the arguments against that for me is the argument, it's called the space travel argument against the existence of extraterrestrial life. And it's often framed in terms of self-replicating machines, so-called von Neumann machines. So imagine it's possible for us, for a civilization, to build a machine, some kind of AI, that's sufficiently smart and capable that it can fly to a nearby solar system, reproduce itself, copy itself, and then send the copy out to the next solar system, and so on. So you have, if you build a one successful replicator, you have an exponentiation of replicators. You have 1, and then 2, and then 4, and then 8, and so on, exponential growth. And you can show that even given our rocketry technology, you can cover a galaxy like the Milky Way in a reasonably short space of time. By reasonably short, I might even mean 100 million years. Right, that's reasonably short on galactic timescales. But the key point is once a single successful replicator has been launched, then it is inevitable that over a few tens of millions of years, the galaxy will be covered with replicators, and we don't see any evidence of them. It's possible that we can infer that if we assume that we could detect them, then the absence of them may allow us to infer that no civilization has ever got to that point. And I think that's quite a persuasive argument. Now, it's possible that there are many civilizations out there, but the advanced civilizations choose to remain hidden. Sometimes called the dark forest hypothesis, the quarantine hypothesis. We've been asked to make moral judgments or judgments on how a civilization will behave, what they will choose to do, and that's of course impossible to judge. But let's imagine civilizations, when they get technologically advanced, also get intellectually and morally advanced. And let's say that they choose, perhaps for good reason, let's say they choose to remain hidden because they don't want to draw attention to themselves. Let's say it's inevitable that if you think about it carefully and you think there are other advanced civilizations out there, then you choose to remain silent. You hide yourself as best you can. It's possible that that's the way that a civilization would think. Maybe that's a logical thing to do. I find it difficult to believe, given human history, that that's the way that intelligent civilizations behave. The idea of black holes goes back a long way, actually, back into the 1780s and 1790s. There were two physicists, mathematicians, natural philosophers, whatever you want to call them, working at the time, that had the same idea, apparently independently of each other, to understand why black holes cause so many conceptual problems. It might be worth just describing very briefly what a black hole looks like. Black holes are interesting because, going back to the work of Stephen Hawking in the 1970s, it turns out that they demand that we think about both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. But the problem has always been, well, is there anywhere in nature that we can look to observe something that requires us to merge those two theories together? And black holes really are the unique place, as far as we can tell, in nature, where we can see a thing just sitting there in the sky that demands that we consider those two theories working together to hopefully reveal a deeper thing. The idea of black holes goes back a long way, actually, back into the 1780s and 1790s. There were two physicists, mathematicians, natural philosophers, whatever you want to call them, working at the time, that had the same idea, apparently independently of each other. One was a clergyman, an English clergyman called Mitchell, and the other was the great French mathematician Laplace. And they were both thinking in terms of an idea called escape velocity. So the escape velocity is the speed you have to travel to completely escape the gravitational pull of something, a planet or a star. For the Earth, for example, the escape velocity from the surface of the Earth is around 8 miles a second, 11 kilometers a second. If you go bigger, you make a bigger, more massive thing, let's go up to a star, for example, like the Sun, then the escape velocity increases because the gravitational pull at the surface increases. And actually for the Sun, it's somewhere in the region of 400 miles a second. It's really fast. What Mitchell and Laplace thought, and I think it's a very beautiful idea, is they imagined in their mind's eye, well, can you go bigger? Can you imagine more and more massive stars, giant stars, such that the gravitational pull is so large at the surface that the escape velocity exceeds the speed of light? And then you wouldn't be able to see them. There's a wonderful quote, actually, in Laplace's paper, where he says that the largest objects in the universe may go unseen by reason of their magnitude. And this is back in the 1780s or 1790s. So he's imagining stars where the gravitational pull is so vast that even light can't escape and you couldn't see it. Dark stars, I think he referred to them as. Now we know that such objects do not exist in the universe in that sense, in the sense that Mitchell and Laplace meant. But actually, they missed something, which is not surprising because it sounds almost paradoxical. But you can also increase the escape velocity, the surface of an object, by squashing it. And it turns out that if you take the Earth and you squash it down and squash it down and squash it down until it's about that big, the radius just less than a centimetre, then the gravitational pull at the surface would be so great that light couldn't escape. And that is essentially the modern concept of a black hole. Now, Mitchell and Laplace's calculations or imaginings were based on Newtonian physics, so pre-Einstein. We come forward to 1915, Einstein published his general theory of relativity, which is a different model, a better theory of gravity. And it turns out that black holes also exists in general relativity. Now, if we come forward to 1915, Newton's theory of gravity is replaced by a better model, a better theory, which is Einstein's general theory of relativity. But the idea that there can be objects that can be compressed such that they trap light is also present in Einstein's theory. The first physicist to predict such a thing, or at least derive the mathematics that describes such a thing as a black hole, although he didn't know that they existed, Schwarzschild. What Schwarzschild did was provide an exact solution to Einstein's equations that describes space and time, the distortion of space and time, in the region of a star, or at least an idealized star, which is a perfectly spherical, non-spinning ball of matter. It's a model, a simple model of a star. Now, Schwarzschild described or discovered the solutions to Einstein's equations that describes what happens to space-time outside such a thing way back, actually 1916, just after the theory was published. What Schwarzschild's solution also describes, though, although he didn't think in these terms at the time, was what that space looks like if you completely remove the star, but leave its imprint in the fabric of the universe behind. And that is essentially the theoretical description or the model of a modern relativistic black hole. Now, while Schwarzschild's solution, and by solution I mean we're to picture a distortion in space and time, a distortion in the fabric of the universe. While Schwarzschild's solution does indeed describe the simplest possible black hole that we can model in the universe, people didn't really think in those terms at all until later. You see in the 1930s, Einstein and a colleague of his, Rosen, for example, exploring that space-time and building models of what that space-time might look like. But I think it's true to say that really, certainly until the late 1930s, and actually arguably post-war until the 1960s, most physicists thought that such things would not exist in nature. So they were theoretically interesting, perhaps not practically interesting. The reason is that you have to create such a thing. So it's one thing to have a model of space and time that describes this object called a black hole, from which not even light can escape. But it's another thing for nature to actually make it. So if you go through the 1930s, there's a lot of papers. Actually, Robert Oppenheimer and a student of his, Snyder, wrote a very famous paper just before the war, which explored whether a real star in the universe, at the end of its life, could collapse and collapse without limit to form this geometry, this thing that we call a black hole. Just before the war, Oppenheimer and Snyder showed that under certain assumptions, a star could behave in such a way. But it wasn't really until the work of people like Roger Penrose and Stephen Hawking and several others in the 1960s that it really began to look as if nature would build these things. There's this great quote I remember with some fondness, actually. Arthur Eddington, a colleague of Einstein's, who was very English, very proper physicist. And he said, "Nature will prevent such absurdities from existing." Just, that's it. Nature will prevent it. Well, it turns out nature doesn't prevent it. We now know, and we've observed them, that stars do collapse to form black holes. And then theoretical physics moves on. So people accept that these things should exist, although it's true to say that we haven't actually imaged one until the 21st century. But in any case, people accepted these things should exist. More and more evidence mounted that they do exist at the centres of galaxies and at the sites of collapsed stars. But then we have to face the consequences. What does it mean for our understanding of the universe if there are these objects where space and time behave in a very strange way, where light is trapped, and where it would seem that anything that falls in is at the very least locked away from the universe forever? So to understand the conceptual problems that are faced if these things exist, then it might be worth just describing very briefly the Einsteinian description, the pure description in general relativity. A black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. The event horizon is very simply and a bit hand-wavingly, but it's a reasonable description. It's just, if you can imagine a sphere in space, and if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape. So the event horizon separates the interior of the black hole from the external universe. The Fermi paradox is this. We know that we live in a big old galaxy, in a big old universe. And let's, for the purposes of this discussion, confine ourselves to the Milky Way galaxy. The Milky Way galaxy, we now know, has something like 400 billion suns. And we now know that most of those suns have planetary systems around them. So trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermi paradox, at its heart, is the statement that, notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox. And I think it's a very good question. It's an extremely good question. And there can be many answers. And the great fun, or the great, I would say the intellectual value of the Fermi paradox, so if we accept that we haven't seen any, so let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, well, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement, so we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So one answer to the Fermi paradox, is the idea that we don't seem to see anyone, is that no one ever evolved. Right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 4.5 billion years old. So we know, as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago. But it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization. 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy, in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. If you think about it, that's a big ask. What I'm saying is, on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to erase, destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened. We know that there have been impacts on the Earth, right? We know that the famous impact that wiped out the large dinosaurs, there's been no impact big enough to destroy the unbroken chain or break the unbroken chain of life for 4 billion years. So maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say it's a property of a solar system. It's not really just a property of the planet. It's a property of the parent stars. But we'll see a bit later why that's a bit of a hand-wavy description. But another description of the event horizon, which confused people all the way through the history of black hole research actually, certainly to the early papers in the 1930s and perhaps even post-war, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. And that's a direct prediction of Einstein's theory of relativity from the external perspective. If you watched, for example, an astronaut falling in towards a black hole, then from your external perspective, you'd see their time pass more slowly, slower and slower and slower, as the astronaut approached the black hole, until on the horizon, you would see their time stop. That suggested to many people in the early days that a star couldn't collapse to form a black hole. It confused them. They thought, well, if a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial early conceptual problems, which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole. So time passes at 1 second per second on the watch of an astronaut falling in, but from the external perspective, time freezes on the horizon. So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole. Now in pure, just in Einstein's general theory of relativity, actually it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not, and is still not, understood. So that's a great mystery. And it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are, we have a problem with the singularity, we don't really have any access to it, we don't have the conceptual tools to explore it, so it may remain a mystery for a century to come. It's not clear what to do. For a perfectly spherical, non-spinning ball of matter, it's the simplest thing you could do, which tells you how space and time are distorted by it. And that's a model for a star. It's the simplest thing you could do. So he solved the equations. It's a remarkable thing. In those equations, there is a description of a black hole, although it wasn't realized at the time. It's a remarkable piece, simple piece of mathematics, actually. So essentially, what's the idea behind a black hole? One way to think about it is that you could remove the star from this fabric, but leave the distortion behind? So if you do that, you get the description of a black hole. We broadcast radio signals out to the stars, the Arecibo message, for example, albeit weak ones. We've launched on our space probes, like Voyager, maps, pulsar maps in that case, which shows the location of our solar system should any other civilization find it. So at least at the moment, we haven't come to the view, which may be a wise view, but we haven't got there, that we should remain silent. Quite the opposite. We've tried at every opportunity to broadcast our existence. Maybe that's because Carl Sagan argued, I think, that a sufficiently advanced civilization, a civilization that can build interstellar spacecraft and communicate across interstellar distances, perhaps is wise enough to have overcome those primitive instincts, the instinct to cause trouble, to fight wars, to colonize, to walk over other civilizations. Perhaps it's inevitable that with technological advance ultimately comes wisdom. But it's a hypothesis. Maybe it is. Maybe it's just anybody sufficiently clever to build an interstellar spaceship will be also sufficiently clever to hide it and not draw attention to themselves. Maybe it's immoral, maybe it's like Star Trek. Maybe it's the prime directive. Maybe it's morally certain that if you're sufficiently advanced, you decide to take the position that you will never introduce yourself or interfere with another civilization. Maybe that becomes a kind of law of nature for sufficiently intelligent beings. Maybe that's conceivable as well. Another explanation for the Fermi paradox might be that civilizations live and die. They rise and then they fall. And because of the sheer timescales involved and the sheer size of the galaxy, no two civilizations ever overlap. I once had the great pleasure of meeting Frank Drake, the Drake equation, a legend, in his house. And he also grows orchids. And I arrived at his house just coincidentally on the day that this rare orchid flowers. And it flowers for, I think, 1 or 2 days and then goes away again for the year and then flowers again the next year for 1 or 2 days. And he used it as an analogy. He said, well, maybe civilizations are like that. So maybe civilizations are like rare orchids, and so they flower and die and flower and die. And just because of the sheer timescales involved, none of them ever overlap. And so there could be the wreckage, the ashes, the fossils of civilizations out there. But of course, we would have no way of knowing until we explore the galaxy and maybe find the ruins of these other civilizations. Who knows? I mean, it's quite plausible if you think about it. Are we going to exist in 10,000 years' time? It's, to a large extent, in our hands. Maybe we're sufficiently stupid that we won't exist beyond the next century. There's an idea in this field, trying to explain the Fermi paradox, called the Great Filter. Now, the Great Filter can lie in our future or our past. So let's think about what it would mean for a great filter to lie in our future. That would mean that civilizations do arise in the Milky Way galaxy and get to somewhere like the position that we're at now. So they develop rocketry, they develop nuclear power, nuclear weapons, for example, they industrialize, but then there's a filter in the future that stops them becoming true spacefaring civilizations. So stops them becoming multiplanetary species and stops them ultimately traveling between solar systems to begin to colonize a galaxy. So why might that be? Why might there be a filter waiting for us in our not too distant future that's going to stop us going onto Mars and stop us escaping our solar system? What might stop us from becoming an interplanetary species and ultimately traveling out beyond our solar system? I don't think it's technology. As far as I can see, I don't see anything in the laws of nature in principle that would stop us from becoming an interstellar species. It might be 1,000 years in the future, 10,000 years in the future, it might be 100,000 years in the future. Even that, right, 100,000 years, it's a blink of an eye in the lifetime of the universe, in the lifetime of a galaxy. So I don't see any reason in principle why we couldn't become an interplanetary, interstellar species other than potentially our own stupidity. And I think that probably it could be one of the reasons why we don't see any other civilizations around.